This is the third in my sequence of videos on conduction, convection and radiation. So I'm trying to describe what radiation is, how surfaces are linked to radiation and how we would investigate radiation in a lab. It's quite common for exam questions to ask you about the practical for radiation, so I'm going to spend a little bit of time on that. So you may have seen thermal imaging pictures like this before. They work due to radiation. So any objects that are not at absolute zero, which is a theoretical temperature, the coldest anything can be, so any temperatures that are not at that temperature, which is all real life objects, emit something that is called infrared radiation. That is just like light, but a slightly longer wavelength. Now the crux of understanding this is that the higher an object's temperature, the more infrared radiation it gives out each second. So if we look at this image, we can see that the cat's eye sockets and ears are giving out the most radiation per second, whereas places like the fur are giving out a low level of radiation per second. Infrared cameras are also used by the fire service, so they can see where the hottest bit of the flame is, so where to address their attentions in terms of putting out the flame. You need to know which surfaces are good emitters and absorbers of radiation. So just to remind you, emitter means how good is it at giving out radiation, absorber means how good is it at taking in radiation, and reflectors are objects that don't absorb radiation and instead they bounce it back out into the environment. So you need to know which substances are the best emitters and absorbers, but sometimes it's useful to compare to reflectors, so we might put this in as well. So the best emitters are black and matte, as in not shiny, surfaces. The worst are shiny. In fact, I'm going to put these in the other order so that the colours are next to each other. White and shiny surfaces. In terms of absorbers, again, the best are black and matte surfaces. The worst are white and shiny. So those ones are quite easy to remember, because if you think about being out on a hot summer's day when the sun is shining, what colour would you not want to wear? Black, because it would absorb a lot of the sun's radiation. So a big misconception with students is that they've got the opposite characteristics, when in actual fact for emitting and absorbing they've got the same characteristics. It's actually reflectors which do the opposite. The best reflectors are white and shiny surfaces, and the worst reflectors are black and matte surfaces. Just an interesting point here, if the best emitters are black and matte surfaces, that really means that the radiators in our house should be painted black. We don't tend to do that in houses for aesthetic reasons, but if you go into some big old buildings, some churches, you will notice that all of the radiators are painted black because they're more efficient that way. So how would we investigate this in a lab? The first way to investigate this in a lab is using this piece of equipment, which is called a Leslie cube. It's basically a cube where you would pour hot water in. Okay, so the internal side of all of the edges are the same temperature, the temperature of that hot water, and then you would take this piece of equipment, which is called an infrared thermometer, and take the temperature of each side. Okay, what you would need to make sure is that the infrared thermometer was the same distance away from each one, and that you did all the surfaces quite quickly so that the internal temperature was the same. And what you would expect was that the black side would be the hottest temperature, because it was giving out the most radiation per second. If you don't have an infrared thermometer or a Leslie cube, you can also do this experiment with a purpose-made can, which is painted black or silver, and if you don't have those, you can take a normal Coke can or a beaker and just cover one in black paper and one in silver paper or silver foil. What you then need to do is fill them both with water that's the same temperature and leave them for the same amount of time and observe the fall in temperature. Okay, so you'd be observing the temperature falling with time. So what would that look like in terms of a set of results? Well, over time, if this was your starting temperature of the hot water and this was room temperature, both experiments would fall down to room temperature, but the one that's the best emitter would get there first because it gives out heat the fastest. So the black one would go down to room temperature first, whereas the silver one would take longer. Those were both for emitting. You also need to know the kind of corresponding setup for absorbing. So very similar setup. This time you would need to shine some kind of heat source at water, maybe a kind of a lamp of some sort. So you would need to keep the lamp at equal distance away from one surface and shine it at that surface for maybe 10 minutes or so. What you would then need to do is measure the temperature rise when shining at the black surface. Then you would need to repeat that, but shine it at the silver surface, shine it at a white surface, etc. And what we would expect is that the black surface causes the highest temperature rise. If you don't have that equipment, again there's an alternative setup, very similar to what we did before. You would need to take a beaker or a can, cover it in black or white or silver paper, and then again shine some kind of lamp, hot lamp at it, and observe this time the increase in temperature. So they would both start at room temperature, and I guess they would go up to a target temperature, which would be different for each experiment, but left long enough they'd get to that temperature. The difference is, again, the one with the black coating would get there first, and the one with a white or silver coating would take longer. So that's it for radiation. We've explained what it is, we've explained how temperature and surface are linked to both emission and absorption, and we've looked in a lot of detail at how you would investigate that in the lab.